Ladies and gentlemen, buckle up your seatbelts because we are going to do a quick reviewing of reaction rates and mechanisms, which were part of our study of kinetics. If we look at this example reaction, how do we communicate the speed of the reaction? What do we measure? Remember we said that we can create what are called rate expressions. What we as chemists have designed is we communicate the speed of a reaction by looking at the change in concentration of either a reactant or reactants or a product or products. And we're going to be measuring mole per liter, that's what the square brackets mean, per unit of time. So for example, we could express it in terms of the N2O5. Again, square brackets, we are communicating concentration in mole per liter, and our time unit is up to the experimenter. It's usually seconds or minutes. So mole per liter second would be the common units for rate. Now, if we be graphing concentration versus time, and we're commonly beginning with reactant, and then we are producing product as the reaction goes. So we begin with none of these. Well, then our graph is going to start with whatever the concentration of that reactant is. However, the graphing is exponential with negative growth or inverse. Concentration plays a role on rate. So as the reaction is proceeding and concentration is changing, rate changes. That's why it takes on this shape. Now, if I'm starting just with reactant, then my products will begin at 0. Because of the ratio of my reactants and products, these will not be the same curve. I'm going to be producing this at 4 times the rate of that. So we should get something like that, but you can definitely tell reactant versus product because of your starting. Now, if we would know or have determined the value of rate in terms of one of our species, and you know your balance equation. So let's say that we know the rate according to NO2. And let's say that the rate is, let's say 12 mole per liter second. Well, if you know the value in terms of 1, you can look at your balance equation. So these are at a ratio of 2 to 4 to 1. So that means the rate of production of NO2 is 4 times that of O2. So if I want to get the rate of O2, it will be then 1/4 the rate of NO2. So the rate, if I know NO2, the rate of O2 would be 3 mole per liter second. And if I know the rate of NO2, and then N2O5 has a mole ratio of 2 to 4, the rate according to the N2O5 would just be half that of the NO2, and so that would be 6 mole per liter second. Now, officially, this should have a negative on it because we know if this is changing, we are ending at a lower concentration than we started, so this will be a negative value per unit of time. But usually rates are communicated with absolute values, but we can be most correct and put that on there. This video will also talk about what is a rate law, really the differential rate law, but we usually drop that adjective. What is the rate constant? What about reaction mechanisms? And then reaction diagrams. So, if you're ready, let's remind ourselves about the differential rate law. So that is rate is equal to the rate constant times your reactant or reactants, and they're raised to a power that reflects the order of that reactant. The order conveys the role concentration of that reactant plays on rate. The most common order is first, then second. We can also encounter zero. We can also encounter half order. Now there are third order and other, but these are just most practically and realistically what we will encounter in our coursework, but also in the AP Chemistry exam. The order of the reactant can only be revealed through experimental data for the overall reaction. Your rate still will have the units of mole per liter unit of time. So commonly we'll see mole per liter second or mole per liter minute. As far as our rate constant is constant per the reaction and per the temperature. So the rate constant changes as we change temperature. Remember, that is a pretty important relationship to remember. You can have something that is zero order, and remember, that just means we need some of that reactant present, but its concentration doesn't impact the rate. So if we would double this concentration, it doesn't change the rate at all. And so if A were zero order, you actually don't even have to show it. We could just write this as rate equals K, B to whatever order we found that to be. All right, so I thought it would probably serve us best if we actually went through a problem to convey the rest of our review to us. So if we take a look at this example problem, this is actually from the NIMSY review packet. They call it a super problem because it's hitting a lot of the aspects within this concept. So we're doing this reaction, generically X plus 2y yielding Z at room temperature. All right, we are doing different experimental runs, varying the concentration of X and Y, and then we are initially measuring the rate in terms of change of concentration of Z with second as our unit of time. All right, let's dig in. Calculate the initial rate of disappearance of Y in experiment 1. Calculate the initial rate of disappearance of Y. So the rate of Y in experiment 1. Well, I'm given constant. Oh, I'm given the rate in reference to Z. 1.20 times 10 to the negative fifth mole per liter second. Do not be skewed or shaken by them conveying these units with the negative exponentials. We know how we could rewrite that. All right, I have my balance equation. Z is a 1:2 ratio with Y. So Y will be consumed at twice the rate that Z is produced. So to get the rate of Y, that will be twice the rate of Z. Now, do we see this command to calculate? So we need to show some kind of work. I'm going to write down that I know the rate of Z and this relationship, and then since I wrote the rate of Z here, I don't have to rewrite it. I can just say the rate of Y then would be 2.4 times 10 to the minus fifth mole per liter second. Golly, with sig figs, I need that. 40. Now, I know when we're first given this information, because we're given initial rate measurements, we think we need to employ the method of initial rates. So be very, very careful. Make sure that we're noticing right off the bat we're given our balanced equation. All right, so next, determine the order of the reaction with respect to each reactant. All right, here's where the method of initial rates comes in. Now it says show your work. So they are expecting for us probably to use numbers, but I bet that you could justify and just speak your way through this. All right, so remember how we do this. We want to find the order of X. So I want to look for an experiment where I'm changing the value of concentration of X, but not of Y. And I always like to go from lower to higher concentration. So if I compare experiment 3 to experiment 1, Y is constant. I'm doubling X, and rate is doubling. So then I know whatever change I make to X to the first power is the impact on rate. So it's first order. But I'm going to go ahead and show that work. So I'm looking for the order with respect to X. So I'm going to call that lowercase a and then the order of Y, B. I like to put a bit larger numbers over the smaller numbers. So my concentration in experiment 1 is greater. So I'm going to put experiment 1 over experiment 3. And so, looking at this, the rate of 1 will be rate constant of experiment 1 times X concentration of experiment 1 times Y concentration of experiment 1. And I'm comparing that to 3. So the rate at 3 will be rate constant at 3, X trial 3, Y trial 3. All right. As long as I've kept the temperature the same and my reaction the same, the K values will be the same. So they're going to cancel. My concentration of Y from experiment 1 to experiment 3 is the same. They're going to cancel. So all I have to do is plug in 1.20 times 10 to the minus 5th mole per liter second over 6 times 10 to the minus 6th mole per liter second. And that is equal to 0.200 mole per liter over 0.100 mole per liter. And what I get is 2 equals 2, forgot my exponent, to the A power, therefore A equals 1, and X is first order. That would be sufficient work to show. Absolutely, absolutely. Now, what we could do is say, comparing experiment 1 and experiment 3, the rate, the concentration of Y is 0. The concentration of X doubles, the rate doubles, therefore X is first order. For Y, to tell, we would do the same thing. So you could lay out the same work, and we would want to compare where we are keeping X constant. So from experiment 1 and experiment 2, from 1 to 2, we're doubling Y. From 1 to 2, we're keeping X the same. When we double Y, Z, as far as rate, doubles. So then we know that Y is also first order. Okay, so you could go through that. All right, we're asked next to write the rate law. So, nice and easy. You just plug in the powers, if you will, that you found. So that would be the answer for C. Calculate the value of the rate constant. They're a stickler for units. So all we would do is choose a line of data and plug in values from that line of data. And remember, I encourage us to choose a line that's either the first given or the last given, because if we choose something in the middle, our eye is probably going to misread one above or one below. So if we want to plug in, let's just say the values given, let's just say the first experiment. So our rate there is 1.20 times 10 to the minus fifth mole per liter second over our 0.200 mole per liter, 0.200 mole per liter. Just be very careful that if these are second order or half order, that you're interpreting them correctly and you're not forgetting those powers. One of our moles and one of our liters cancels. Numerically, we will have 3.00, and our units will end up being times 10 to the minus fourth liter per mole second. Remember, we talked about how we can check ourselves to make sure we have the correct units on K. We know that rate is mole per liter second. We know that. And so to yield this unit for rate, what does K have to have, knowing X here is mole per liter to the first and mole per liter to the first? Well, we absolutely know that K will deliver our unit of time. But we need to cancel one of our moles and we need to cancel one of our liters. And look at that. Ta-da! There's our value. Okay, so that's a reminder about the method of initial rates. All right, ladies and gentlemen. Well, what about mechanisms? Now, remember, you will never have to come up with mechanisms yourself. So remember, we determined that the rate law experimentally for the overall reaction has X to the first and Y to the first. All right. What we have to do is often see if a mechanism is possible. And it's possible, remember, if it passes two tests. If the elementary steps, those are the step-by-step processes which take us from reactant to product. So if we add up our elementary steps and they yield the overall reaction. So the elementary steps add to yield the overall reaction. And then two, that the rate law of the mechanism matches the rate law of the overall reaction. All right. Well, we determined what the rate law of the overall reaction was above. So we're being asked to select the one that is most consistent with the experimental data. Justify your choice by writing a rate law for each of the three mechanisms. All right. Now remember, reaction can only be as fast as its slowest step. So we take the cue from the slow step. Let's go in reverse. For mechanism 3, our first step is slow, second is fast. So remember, from an elementary step, the rate law can be written right from the molecularity. The balance equation, or the number of each reactant molecules, equals the order. So there's only one X, first order. There's one Y, first order. Well, ding, 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 ding. This mechanism is looking good. But let's check ourselves. Okay, the second mechanism, slow, fast, fast. All right. The rate law is written just from that slow step. Oh, this does not match the experimental overall rate law. So the mechanism is not possible. Well, let's look at mechanism 1. Okay, I see my slow step. But it is preceded by a step that is fast and in equilibrium. So it's going to just take a little more work. Okay, so the rate for the slow step will be K, X, D. First order, first order. But the problem is, D is a reaction intermediate. It is produced as a product but then consumed as a reactant, they will be canceled and not show up in the overall reaction. There's a problem with this rate law of the slow step that it includes that. Now, if it was just preceded by fast, we'd be done, and this would not be possible. But since it is fast in equilibrium, remember, equilibrium means the rate in the forward direction equals the rate in the reverse reaction. So the rate of the forward, I'm just going to put a lowercase f for the rate of the forward, would be K y, or we could say y second order. The rate in the reverse will be equal to d first order. Since it's an equilibrium, these are equal to each other. Y first order, k, d. We know these are different k's, but they're constant. So I want to solve this expression for the reaction intermediate. So I'll divide both sides by the k of the reverse reaction, but the forward minus or divided by the reverse will just be a new k value. And so that is equal to concentration of D. I now plug in. So the rate law from this mechanism will be K X. Now I'm just going to, plug in this other K. It's just going to make a new K value. Y squared. That doesn't match. So we would say this mechanism not possible. The rate law does not match the experimental overall rate law. All right, so that was good that we got to go over that. All right, next, identify substance D in the mechanism shown above as an intermediate or catalyst. All right, reaction intermediate shows up first as a product and then is later consumed in a later elementary step. So it would cancel out and not show up in the overall reaction. An intermediate is seen first as a product. A catalyst is seen first as a reactant and then is produced and doesn't show up in the overall. So D, reaction intermediate. Here, reaction intermediate. G is also a reaction intermediate, and D a reaction intermediate as well. We do not have any catalyst shown here, but let's just say, that if we had A and then we reproduced it'll cancel out and not show up, but we saw it first as a reactant, then it's a catalyst. Okay, just slightly more. Okay, reaction diagram. What do we know about this? I pray that you don't even hesitate to say that, okay, that is exothermic. So here would be the enthalpy of the reaction. I'm starting with reactant here, ending with product. These can be energy, potential energy, enthalpy, and this is reaction progress. Okay, they're asking us to label activation energy. Remember, that is the size of our hill. You could label it activation energy, but if we remember, we usually represent it with a capital E, a subscript A. So there's our activation energy, there's our enthalpy. It says draw a second energy curve showing the effect of a catalyst. Now I luckily have a red pen here. You could do a dash line or a darker line to show that, but we know a job of a catalyst is to lower the activation energy. So I would want to indicate that somehow. It just has to be a lower height of hill. Then, just the last here, the collision between X and Y occur with enough energy to overcome the activation energy barrier. However, no products are formed. What other factor? Okay, remember collision theory. That's our whole cow. The, bull wanting to do his thing with a female cow. Remember, It's not just coming together with sufficient energy. They need to have correct orientation. So it could be that the molecules are overcoming the activation energy, but they're not colliding as they need to break bonds or form the activated complex or something else. Okay, that's a nice review, ladies and gentlemen. I do want to show you, I have worked out another sample problem for us. So if you would like to take a look, here's an exam from 2010. If you want to pause it, take a look at some of my work and answers. And then there was a question that talked about the impact of different variables upon the reaction rate. So if you want to take a look, pause, look at how I responded, and that just helps to review a couple more things dealing with kinetics. Good luck.